Okay, so here, if you look at this basic equation, what is happening to the current as a function of time? It's decreasing, right? And therefore, if the current's decreasing, what's happening to the B field generated by the current? It's decreasing. So what's happening to the flux in this loop? It's decreasing, right? The flux is decreasing, and it is decreasing out of the loop, right out of the page, right? So then, the induced current is going to do what? What's it trying? What does Lenz's law say? Fight the change. So if it's getting smaller coming out of the page, then we need to make it stronger. So we need to put our fingers out of the page. And that gives us a counterclockwise current. Oh. Yeah, go use your left hand.
Okay, wait. Oh, okay, yeah.
Yeah.
How do you initially know that it's going to come out of the
Flux or light. Yeah, here's the wire, right? Or here's the current. This is the current. Fingers wrap around like this, right? And then, all right, how are we doing? Good. Questions?
So this is a bit quick.
Yeah.
So how do you know like exactly where the magnetic field is? Is it because like you did the light?
This is the wire. That's the wire. This is the loop. You put your fingers on top. Which way they point? Yeah, out of the page. So that everything above this is out of the page. That's why the flux is out of the page. And then below your fingers is always pointing in. Yeah.
So that means there's dots. Dots inside the loop.
Yes. So what I would do is if I was doing this with some sort of diagram, I would say like this. And it goes on to infinity, and that goes on to the test. John, all paper. There you go. Okay, question? Does that make sense? Okay, very good. So now we move on. Justify your answer would be, the justification would be the current is reducing as a function of time. Thus, the B field and the flux is reducing as a function of time. Lenz's law says to fight the change, right? So then, or you can just say by Lenz's law and the right-hand rule, that's it. You don't have to like quote them. You can just say by Lenz's law and the right-hand rule, that's it. All right, then B, indicate whether the light bulb gets brighter, dimmer, or stays the same. Okay, what do you notice about the rate at which the B field is, at which the current is decreasing? You see that the B field, you see the current is decreasing by a constant value, which means the decrease is linear. Does that make sense? Do you see what I say when I say linear? It means it's the decrease is constant per time. If that's true, then the change in flux should be constant per time. And if the change in flux, if delta phi is constant per time, then that means the rate and therefore the induced current gets constant. You know what I'm saying? Because it's about the change, right? The change is what generates the current. If the rate of change is constant, then the current that is being generated will be constant. I mean, obviously it can't be constant forever, because it's going to start at some value and it's going to go to zero. And when that happens, okay, then it can't be constant anymore. But in the time that we're looking at, this has a constant value. The change has a constant value, which means our flux is constant, like the amount it's changing is constant, therefore our current is constant. So it remains the same. All right. Then determine the magnetic field at T0 due to the current in a long wire at distance r from the long wire. Yeah, we just use like Gauss. Yeah, yeah. No, that's all right. What was that? Counterclockwise? Right now? Yeah, okay. Yeah. Now, here's the thing, right? If you took my class, if you took honors last year, then you know that's the formula that we use for for magnetic fields. You put that down, boom, 2 points.
So you don't even have to integrate it?
Should you just know that?
Yeah, like I've said before that if you were a good honor student, you could probably pass the calculus-based exam, just because. Yeah. So anyways, yeah.
Average student, average regular student.
But then it just depends on how hard you work. But anyways, if we look at this integral of b dot dl, they're just using like the cylinder around the length and then going through it. It's pretty straightforward, actually. All right, then what's that? Oh, that's a surface integral, right? It's not a volume integral. Does that make sense? Yeah. Okay. All right, then let's do. We do that. This one. Derive an expression for the magnetic flux through the loop as a function of time. So if the magnetic flux is a function of the current, then we just have to make sure that we stick the current into Gauss's law for magnetism. Right? Or just the definition of flux, right? Then we just plug in the chain, the radius or the B field, and then we have a statement for what's happening to I, and then that allows us to come up with the final answer. Yes, questions? That's most of these.
I know.
In regular, they all are in honors. They all use numbers. Yeah. Wait a second. Substitute. Which one? Oh, this right here. Okay. So if we're taking this over an area, the question is, what is the area through which this flux is affecting? Right? Does it make sense that the area through which this flux goes is this? Does that make sense? So what is this area? This area in general, of course, is BA, right? But then we're looking at it like we're calculating some distance R from the wire. Does that make sense? So then we're taking dA is some really thin slice of this area. And then that means dA is B times the dr, which is a really thin piece of that R.
So it's not actually A, it's actually R.
Well, it's just, how do you describe it? It's the same thing, it's the same concept when we did rotational inertia, right? We said, I want to find the sum of all the torques caused, or all the moments of inertia caused by each individual piece of this thing. So now we're trying to say, I want to know the flux caused by each little piece of this area. So how do you describe the area? Like this, with the differential unit of the radius, right? Swiping out, so each little slip of R swipes out another piece of this. And then when we add all those up, we get our flux. Does that make sense, Jess? Cool. Oh, whoops, sorry. Okay, any other questions on that? We're good? All right, and then finally, driving expression for the power. That, of course, is the no-brainer question, because if you know, if we've already calculated d phi, like we've already calculated what phi is, so we can just take the derivative of that and get the flux. I mean, take the flux and get the EMF. And once we've got the EMF, just plug it into E squared rho. So they're just using this power equation, which comes from P equals IV, and just substituting it. All right, questions on that? This one, yeah. These two problems are, in terms of their general concept, I think they're not that bad. In terms of doing the math, it's challenging. But like we said, like these are question 3s. So generally, they try to make question 1s more kind of accessible, and then question 2, and then question 3s are usually the ones that require the most work. Okay, and then if we take a look, because you were asking if you were asking what's going to happen for the test, it's always the same. The first question is going to be on electrostatics. The second one